In this example, we're going to numerically solve the second example we looked at, where we had to create the state space form for the ODEs that we came up with. In this case, we had two dependent variables, x and y, and their derivatives x dot and y dot. So we came up with two state variables, x1 and x2. In this case, looking back, x1 was the variable y, x2 was our original variable x. So we want to solve for both of them over 30 seconds of time. If we have initial conditions that y of 0 is -1, x of 0 is 4. And then we're also going to look at them in phase space, which I'll get to in a minute. So again, we have to start with a new M file that's going to define what I'll call x dot. And I'll call this ODE, for example, 2. Again, this only is going to take our independent variable t, our dependent variable x. And let me save it. So I want to pre-allocate it as a column vector. And here, the first one, x dot of 1, or x1 dot, as we have in our equations here, is going to be 1/2 times x of 1 minus 7 times x of 1 divided by 4 times x of 2 plus 4 times the cosine of 2 times t. Now this in particular by hand would be very difficult to solve the closed form solution for x and for y, but that's why we're using the numerical solution, because we will be able to get a solution for that. And x2 dot is just going to be 4 times x1. Alright, so we have the function ODE for x2 that's going to be assembling x1 dot and x2 dot for this state variable, or this collection of state variables. So to run this, I'm going to get t and x, ODE for 5 at tx, and this one's going to use ODE for x2 tx. Here the time span, they tell us they want 30 seconds. And our initial conditions, x1, which is y, is initially -1, and x2, which is x, is originally 4. And we see we get a whole bunch of t timestamps, 82, almost 8,300 values, and x we get two columns for, one for x1, one for x2. So here I want to plot them both. I want to see x versus time and y versus time. But I want to know which one is which. Again, the first column is my values for y, and the second is my values for x. So here the orange is my values of x, the blue is the values I have for y. So one thing we want to check here, remember those initial conditions, y of 0 is -1, x of 0 is 4. Well, in the blue one we see that time is 0. It does indeed start at -1, as it has to, because that was our initial value when time was 0. And here the orange one, x, does indeed start at 4. So it does adhere to those initial conditions that we set forth at the beginning. And then we see it's this kind of periodic function that goes up, comes back down, goes up, comes back down. And that's happening because we're forcing it with the cosine function, but that's not terribly important for the moment here. So this plot is plotting both of our dependent variables versus time. And I'll make this figure 1. Now what we also want to look at here is what we call a phase portrait or a phase space plot, or the phase plane plot, a lot of the same thing, but phase is the operative word here. Here, we don't actually have time appear explicitly. What we do in a phase plot, or a phase portrait, is we're going to plot the dependent variables versus each other. So I'm going to take just the first column of x, and I want to plot it versus the second column of x. And in here, that means that the first column, the horizontal, is going to be y, and the vertical is going to be x. Right, so applying this, I get a much different picture of what's happening in figure 2. Again, I'm plotting my y versus x, so it does kind of move over time and then kind of curls up here and goes in this this cycle, but we don't see time as the x-axis or the y-axis here. We're applying the dependent variables, again, just versus each other. So again, just want to recap. First thing is I make that separate M file that defines my x dot terms. In this case, I have an x1 dot and x2 dot. Pre-allocate, make sure it's a column vector so that it works. Then use the definitions that I wrote on paper that use the state variables and probably time. Then in my main code, I have to call that same function using ODE45, give it the time span, give it those initial values, and then again, my output, x, is going to be a matrix with as many columns as I have state variables, as many rows as I have timestamps. In this case, I can also break this down to solve it at specific points in time, like I did in the previous example. So if I do one at every 0.1 seconds, we see that the results, it actually shows more points when it did it itself. So that's going to be a little bit rough. So if I choose more points, it gets smoother, but it's still actually fewer points than it decided to use itself here. And if I use too many, it's probably going to take way too long to run. Okay, so that didn't take too long. I have those 3,000 points, but I'm going to stick with, usually, for our purposes in this class, whatever it decides to run. So here, 8,000 points. It made the best judgment of how many points to use and where to put those extra points.